Part 2. Graphical description of particle vibration. In Part 1, we learned that different particles have different displacements at a particular time. And what about the displacement of a particular particle? How does its displacement change with time? A displacement time graph shows the change in displacement of a particular particle, and therefore the displacement of a single particle at different times. When a wave travels through, particles are set into vibrations. All particles simply vibrate about their equilibrium positions. For example, for the transverse wave traveling horizontally, the particle vibration will be vertical. It moves up above the equilibrium position and then down below, and finally returns to its equilibrium position and then repeats its motion. So, up and down, and up again, as in its own displacement time graph. A displacement time graph shows the amplitude of particle vibration and also its period directly. And of course, they also equal to the amplitude and period of the wave respectively. So how can we draw a displacement time graph from a given displacement position graph? Or vice versa? Let's take a look at example 5 below. Example 5. Drawing displacement time graph. First, we need to know the amplitude and period of the particle vibration, which are shown directly on a displacement time graph. Here we may calculate the period from the given frequency. Next, the most important thing is the movement of the particle under investigation. Now, when the wave propagates to the left, particle P will first move downward. So the displacement time graph will look like this, just like a negative sine curve. Example 6. Getting the ST graph from the ST graph. So, a displacement time graph is given. How to draw a displacement position graph? First, we need to know the amplitude and wavelength, which are shown directly from a displacement position graph. Next, the most important thing, determine the displacement of at least one particle at that particular time from the given information. Now, particle P is 0.9 meter from the vibrator and hence 1.5 wavelength away. Its displacement is 0 at 0.8 seconds. So we mark this on the SD graph. Lastly, which is the most difficult part, from the motion of particle P a very short time later, deduce the displacement position graph. From the given displacement time graph, we can see that particle P will move downward a short time after t equals 0.8 seconds. And so we may tell a trough is moving towards P at t equals 0.8 seconds. Thus, the displacement position graph can be completed. Exam link 2. Transverse wave on a string. Okay, it is not quite a straightforward question. I suggest you to try it yourself now without looking at the solution below, and then continue this video for my explanation. Part A is straightforward. For Part B, note that particle P starts its motion 1 second after the vibrator starts, and it also moves downwards first, as according to the shape of the wave shown above. Lastly, the period is 0.4 seconds. And so, from t equals to 1 second to 2 seconds, it is 2.5 periods. For part C, the answer is upward. For part C, the answer is upward. At t equals 2 seconds, particle P is at its equilibrium position. It is moving, and moving at the highest speed, upward to form a crest very short time later. For part D, wavelength is not given, but we know it is the distance traveled in one period, and so we may get the answer. For part E, you have two approaches. Number 1, you may deduce the waveform, which is the displacement position graph, from the displacement time graph in part B, which is known to be difficult. Number 2, you may deduce the displacement distance graph from the given picture. But beware that the picture is not drawn in scale. In fact, 1.5 meters equal to 1.5 wavelengths. And so the waveform at t equals to 1 seconds look like this when the wave first arrives at P. Then at t equals 2 seconds, which is 2.5 periods later, look like this. If you insist to use method number 1, you may first find the displacement of P at t equals 2 seconds, which is 0, and hence you may mark this point P here. Lastly, from the motion of P a very short time later, deduce the displacement position graph. As P will go upward soon afterwards, there should be a crest approaching P, and hence you may sketch the displacement distance graph in this way. Do check point 7 on the next page.